Okay, so this is the second example. It's a nice trigonometric example. So first thing I do is I think. I know that this is a sine cosine graph, so I expect some behavior of that wavy, right? I also need to put this is on the interval of 0 to 2 pi. That was given. That interval is given. So we're going to call it closed because it was given. Okay. So on 0 to 2 pi, so I don't need to worry about the limit as x approaches positive or negative infinity because we're just doing a 0 and 2 pi. And I know y at 0 is going to be -1. And I know y at 2 pi is going to be the same thing. So I don't need to worry about negative infinity to positive infinity. I know there's no asymptotes. I know that it's continuous. So I don't really need to worry about domain and range. I don't know the domain off the top of my head. I'd have to think about this because this squared behavior, well, not domain. The domain is 0 to 2 pi right there. The range, I should say. I'd have to pause and think. I know it goes to 0 and -1, but I don't know necessarily where the critical points are, which that would give me an idea of range. So I'm going to let that rest for a minute because it's not easy. I also can't come up with a 0 really easily. So where does 2 sine of x minus cosine squared of x equal 0? That means where 2 sine of x equals negative cosine squared of x. I'm not saying there's not a 0 in there. In fact, I would think there'd have to be, depending on where the graph is happening. You know, I would think there'd have to be a 0, but algebraically, that doesn't make sense to me. So kind of the theme of this is that you don't have to know everything, but I'm at least going to pause and reflect on what I do know and what I can pull out easily, just to kind of think more deeply about the graph and what we can consider. So at this point, I'm going to pause, flip to the next screen, and I'm going to come up with the work for the derivatives. Because this part of it is a little bit hairier in terms of finding the critical points and the points of inflections. In particular, the points of inflection I think is pretty tricky. Okay, so I first want to show you this first derivative, CP. This one's the easier of the two. I think the derivative is fairly straightforward. I had to do just a single flip over here. And then this is chain rule right there. So that goes down to right here. So if you need some color coding, this and this go together, and this go together. And that positive flips over because when I find the derivative of cosine and get negative sign, that's where it flips from negative to double negative to positive. So then I factored out the cosine from both pieces. So I have the cosine there. And then I get my first root and my second root. And my first root happens at pi over 2 and 3 pi over 2, because the 2 just divides out. That 2 just divides out. And then -1 at only 3 pi over 2. But what I do notice, I get this 3 pi over 2 twice. And then I begin to wonder, like that's my first inkling that this 3 pi over 2 has something interesting, that I end up with some multiplicity happening there. So I'm going to shrink this down, and I'm going to bring up the second derivative, because that actually takes a little bit of algebra trickery. So here is my second derivative situation, and I want to explain the steps one by one. This is my second derivative right here, like raw, uncut, no simplification. So then I did some basic simplification with the sine x, cosine x, and got cosine x squared, sine x squared, and put the negative in the middle. So then I got this identity, and the immediate question I get is, oh, would I need to know that on the test? And my immediate answer is, but wait, remember I said this was a take-home? So you'd have every opportunity to look up this identity. And how I knew to look it up was like, this isn't working for me. I need something more. So would I expect you to know this for a test? Probably not. But on a take-home test where you have the resources to look it up, sure, I think that's very fair and valid. So then I was able to change it to that. I distributed out that 2, and I get -2 sine x plus 2 minus 4 sine x squared. And then I'm stumped. But I realize I've got an x squared, an x, and a whole number. And I think, gosh, this looks a lot like a polynomial. So let me go ahead and do a simple substitution. Sine of x equals u. So it looks like this. And then it suddenly looks like a trinomial that I know how to factor. I do factor by grouping. I think this is what Mr. Quinn uses. I'm not quite sure what Miss Williams uses, but I did a factor by grouping, broke it up into 4 terms, factored by grouping, came up with this, and I put my sine x back in, and I got my 2 roots. So that was tricky, but fair, especially on a take-home situation. I think that would be valid. So again, though, I get pi over 6 and 5 pi over 6 because I want where sine of x is 1/2, and that's going to be at that pi over 6, and then on the other side, in both places, we still have a y that's positive. But 3 pi over 2 shows up again. So this is one of the situations where we talked about what happens when a CP equals a POI. It does happen. It's not common. But what does that look like? So I have 3 pi over 2. And I'm sorry, I'm going to close the door here in a minute because my son is playing video games on this snow day. My husband's working from home. So hopefully the voices aren't trickling through too much. But 3 pi over 2 shows up a time again. So I am now going to structure the table now that we have all these values. I have my CPs. I've got my POIs. And I can go ahead and put together a table. Okay, so here is my table. Let me explain how I structured it. There are my endpoints. I labeled them as endpoints because they're not as to infinity. There's no limit, so I don't go down or up forever or whatever. I have that endpoint. So then I have a place for my point of inflections. But what I did over here, notice I have a CP and a point of inflection. What's different here? Well, around my point of inflections, I put a 0 at the f double prime. Point of inflection, 0, f double prime. I drew a circle around the f prime because I wanted to indicate, hey guys, I don't know what's happening there, but it's weird. So I'm going to go ahead and maintain consistent behavior around those points. Same here, critical point, 0 at f prime, but this should maintain consistency. Here I left a question mark. This is just a little note to myself. It's between f prime and f double prime. Like, I don't know what's happening here. But I did list f values at all those critical points for easier graphing, including the endpoints. It's going to make it a lot easier to put it to a graph when I'm ready. So this is my table. One thing I didn't include up in the top was what values are in between. That was kind of tricky. I think I included, if I look at my thing, I included a pi over 8 here, just because there is no standard value, and I popped that in my calculator because it doesn't really matter, right? And I did pi over 4 here. I did a 3 pi over 4 here. I did a pi here. And then I did a 7 pi over 4 here just to get a value. So, all right, I'm going to pause, fill in the table, and then let you do the same. All right, completed table. Points of interest are not very many. It's pretty consistent of what I expected, but this column is kind of the new piece. What happened is I saw that I went from negative to positive, which indicated my minimum, but that I went from positive to positive, which means my concavity didn't change, yet I very clearly got that point of inflection. Remember, this is the value that I had show up 3 times, twice in my critical points and once in my point of inflection. So what's indicating there is I recognize that by that flattening. It's going to be a flatter minimum than normal. It's going to stay a minimum for a period of time, indicating that there is a horizontal tangent line, which is why the double negative showed up there, or the double derivative showed up there as 0 as well. So it's like a significant minimum, so to speak, like a point that it really winds down. So I'm going to shrink this and graph in real time. Okay, recall, world's worth stylist, so I do my best, but I have no promises. All right, so I'm going to graph. I'm going to graph in pink again because that's easier to see. So it looks like at 0, I've got a -1. So there's my 0, -1. And then I have an endpoint at 2 pi also at -1. So I'm going to put my endpoint there. I also have pi over 6. Well, if that's pi over 6 is less than pi over 4. If I broke it into 6, it would be like 3. I don't love that they did this. It would be something like that. 1, 2, 3, 4, 5, 6. So 1 pi over 6, or pi over 6 would be 0.25. So it looks like right there-ish. Okay. And then pi over 2, that's easier to find. Pi over 2 is 2. And then 5 pi over 6. Oh, goodness. All right, so 5 pi over 6 is more than pi. So again, let's break this in half. And then 1, 2, 1, 2, 3, 4, 5, 6. So then I'm going to use, there's, oh, I suppose 5 pi over 6 is actually right here, so I probably didn't need that. 5 pi over 6 is 0.25. Right there. Sorry, I guess I didn't need those on the right. My bad. And then 3 pi over 2 is negative 2, so right there. And my graph is looking like it might do something. I can kind of see that sine wave, cosine wave. Okay, so now let's connect the dots. I have an increasing between that negative 1 right here. And then I have, it's concave up, and it's supposed to shift to concave down. So I'm going to do a kind of, to show my teacher that I know that this is concave down versus concave up. Notice I did a nice little wave. And then this is supposed to be a max, so it's going to swoop down. It's going to continue to be concave down. But then it's a point of inflection, so I need it to go back to concave up. And remember, there's that weird flattening, so I'm going to really exaggerate that flat bottom to show you that it's a horizontal tangent line. Okay? So when I draw these, if I'm drawing them for the teacher, I'm definitely going to accentuate my concave downs as much as I can if I'm not grabbing on a terrible stylus versus concave ups versus concave down. And I really exaggerated that flattening to get that graph.